hi, everyone. Well, thank you for coming. Before I get started, I want to preface my talk with two different things. First of all, everything I'm going to talk about today is research-based. I am not here advocating for anybody to start writing things in WebAssembly anytime soon. A lot of what WebAssembly is today is pretty beta, if you want, or pretty alpha, depending how do you define this stuff. And I would say WebAssembly outside the browser is still probably not as production ready as you will want it to be, right? So this is just a research project out of curiosity, and also because I work on Kubernetes, and there is quite a lot of movement happening in the Kubernetes world around WebAssembly itself. So think about this as like a nerd nerding out about nerdy stuff, right? This is not, I'm actually not even paid by my company to talk about this stuff. I had a tough discussion with my manager to be here. My name is Abdel. I'm a developer advocate at Google. I mostly work on Kubernetes. I do actually host a podcast called the Kubernetes Podcast by Google. And the research that went into this talk and all the demos and all the code is done by me and a colleague of mine. And it's mostly because there is so much happening in the Kubernetes world itself, and also stuff around WebAssembly. And there is a little overlap right now between the AI world and WebAssembly itself that made it just interesting for me to kind of explore this topic, right? So I'm going to tell you a bit about what's happening, a bit of what the future might look like, and then we can have a discussion. I don't think I have enough content for 15 minutes, but we'll see. Before I get going, a lot of work that I'm going to present today is based on a colleague of mine work called Mete. So he's based in London, and he did quite a lot of demos and quite a lot of like the slides themselves. And I just took his things and shamelessly presented them and added my own things to it. But let's get going. What is WebAssembly, right? So WebAssembly is essentially, most of you know it as a browser-based technology, right? A very long time ago, when people started, when there was this web-first movement to turn everything into a web application instead of being like a heavy or like a heavy application. So the web was essentially JavaScript, CSS, and HTML, right? And there was a need at some point for being able to do things much faster than JavaScript and much more natively than JavaScript allows to do. And so some people got together and decided, OK, we're going to invent or create a technology called WebAssembly. And WebAssembly was essentially a sandbox environment inside your browser that would allow you to run native code. And when I mean native code, I mean non-JavaScript code, right? Whatever native means for you. So C++ usually, Rust, whatever. I mean, when this was invented, Rust didn't exist, but like you get the idea. So it started initially with things like, for example, if you want to do it's not the case anymore, but at the time, it was if you want to do a meeting, right, in the browser, you needed a way to access the camera and the microphone on your laptop. You cannot do that with JavaScript. You couldn't at the time, so then you could do it with C++. Now you can with something like called WebRTC, Web Real-Time Communication. It's a set of APIs in modern browsers that allow you to access camera, microphone, stuff like that. But now it's things like if you're using, I think most of you have a MacBook, the new MacBook-based chip, right? Like the M1, M2. Have you seen the reaction thing, the reaction feature in Mac? Like if you are in any meeting, doesn't matter, Zoom, Meet, Google Meet, whatever. If you can turn on reactions and you can do this, and there's like a little thumbs up that goes up, right? So that's actually based into the MacBook, and that's all WebAssembly based. And it's very funny because when this feature actually came out, I think Apple turned it on by default. And there was a lot of very awkward meetings when people were sitting down talking, and then they were doing this, and then there was like bubbles going up, and this was all WebAssembly based, right? So it's basically a binary instruction format where it's basically a compilation target. That's what WebAssembly is. The idea of WebAssembly is that it's a portable compilation target. So a lot of these modern programming languages, including Java, Rust, Go, whatever, they can actually compile toward Wasm or toward WebAssembly. And then you end up with a binary that you can basically execute anywhere where you have a Wasm runtime. How many here are Java developers? Right? Okay, so if this sounds very familiar to GVM, it's kind of like the same idea, right? So this is what GVM tried to do 40 years ago. So yeah, originally it was trying to focus on augmenting browser things, like with JavaScript, like doing stuff that JavaScript can do faster, like 3D animations, games, etc., etc. And it's kind of like today is basically default in all modern browsers, right? So this is WebAssembly inside the browser. So there's this tweet actually from Solomon Hykes, the guy who built Docker, which basically says if Wasm and WASI, I'm going to explain what Wasm and WASI later means. If these things existed in 2008, they wouldn't have invented Docker. Because the whole point of Docker or containers was to create a portable format for building code, right? And so Wasm is essentially trying to do the same. And there is a very funny, we're living in a very funny, interesting world where right now there is like kind of synergy between these two things, because Docker themselves, they released Wasm as a target environment for Docker containers. I'm going to explain it. Just wait. It sounds funny. It sounds like, why would you have a target compiling like thing and then still stick it inside the container? I'm going to explain to you why. But anyway, this was very interesting. There is a report coming out of the CNCF in 2022, which talks about the future of WebAssembly. A lot of the work that is happening in trying to standardize Wasm or WebAssembly outside of the browser, so WebAssembly as a backend technology, is done under an organization called the Bytecode Alliance, and it's a sister organization of the CNCF, right? So it's basically a project under the CNCF that is trying to put together the standards, right? Like they're writing the specs, essentially. They are reinventing Linux, in a way. They're actually reinventing POSIX, right? So, because, again, all of this is pre-new, so there's a lot of things missing. So let's talk about it. So the project to take WebAssembly and run it outside of the project of the browser is called WASI, WebAssembly System Interface. And the reason why is it called WebAssembly System Interface is very simple. If you take WebAssembly and you run it inside the browser, right, you can do pretty much anything, right? You can, you know, you can write whatever code you want. The only two things, or the two things missing, are I/O and network, right? And so WASI, WebAssembly System Interface, is the project that is trying to put I/O and WebSockets or network into WebAssembly, right? So WebAssembly as a runtime exists, and that can do a lot of things, but it's missing the two crucial things that makes it a valid backend technology, right? You need to be able to talk to the network, and you need to be able to write and read from file systems, right? So that's WASI. And so the whole idea is basically, instead of running apps inside the VMs or a container, you can run them inside a WebAssembly runtime, right? So you write code in whatever programming language you want, you compile it toward WebAssembly as a module, and then whatever laptop or computer or server you want to run on will have a WebAssembly runtime, and then on that runtime, you can run your code, right? So it's faster because it's compiled down to almost instruction formats. It's very small, and it's very secure. And the reason why it's secure is because WebAssembly itself was created with the idea of sandboxing the code inside an environment, right? For example, if you are, I can give you a very stupid example, is if you are running on your browser, every single tab is actually separated. It's its own process, and it doesn't have access to other tabs. And if you are, which you all have gone through COVID, if you try to share your screen, you have to explicitly give permissions to one tab to grab a different tab, right? When you're like on Zoom or whatever, you're trying to share your screen, right? So this explicit permissions is kind of one of the features of WebAssembly that makes it, or Wasm, that makes it very, very interesting. So it's faster. There is no cold start. It's really, really fast. I'm going to show you later. It's small because you basically compile down to the almost instruction formats. There is this blog by Frankel, who basically built a Rust application, put it inside the container, and sort of compared the sizes. And you can see there in native formats, the container was 7 megabytes, but in Wasm it's like 2 megabytes, right? So it's really, really small. The end container, It's secure because, again, it runs in this thing allowed by default, denied by default, and you have to explicitly allow the Wasm runtime or the WebAssembly runtime to do certain things. And it's portable. So what do we mean by portable? This is the most important thing, or interesting thing. If you run a container, if you build a container, you have to build toward a specific instruction format. So if you run toward x86 or toward ARM, you have to build a container for that specific, architecture. You can do multi-arc containers, but I don't think that's really a good idea. With Wasm, what you can do is you compile a Wasm module, and it's the runtime that implements the actual architecture of the computer that you run on, right? So you basically, it's more portable essentially than containers, right? Is this the future? This is I think this slide is important to get ahead of time, and usually if a speaker is talking about this, they will leave this slide until the end to kind of inspire people. I want to put it ahead of time. We were doing hardware. Now we're doing hardware with VMs, and now we're doing containers. I don't think VMs are going anywhere anytime soon. I think we're going to continue doing VMs for the foreseeable future. I think Wasm is potentially going to replace VMs or containers essentially in the maybe next 20 years or something. Nothing that is, I'm looking around, there is quite a lot of oldish people like me. So I don't think that we have to worry about this stuff, right? Like we're going to have a job, it's fine. But like it's eventually going to become a very important compilation target / runtime for applications. So to kind of sum up, where we are right now is very interesting. So there is this company called Fermyon, and they basically do, they have a serverless environment, which is Wasm first. So they have basically a function as a service or container as a service, whatever you want to call it. They have their own framework called Spin. I'm going to probably try to show it later. I don't know if I have it installed, but we'll see. But they did this pretty interesting slide, I think, or pretty interesting article. Basically, Wasm has applications across multiple use cases. Browser is the old one. IoT is also pretty old. People have been doing Wasm in IoT, so low-end devices. You can run Wasm there because it's pretty fast. Plugins and edge. If you are, for example, there are two interesting use cases for plugin and edge use cases for Wasm. One of them is Cloudflare workers. If you are a Cloudflare customer, you can you can actually build Wasm code and then give it to Cloudflare, and they will run it on their edge workers. So they can pre-process requests before they come to your application, right? That's kind of proprietary. It's Cloudflare implementation. The one that probably is more interesting to you is Envoy. Anybody here doesn't know what Envoy is? Okay, you don't know what. Okay, Envoy is a proxy. It's a proxy that was built by people from Lyft, the company, right? The Uber-like company in the US. They built an Envoy, a proxy called Envoy, and it's open source and it's part of the CNCF. The key difference that Envoy has compared to other proxies that you might know, like HA proxy, Nginx, whatever proxy, Apache, whatever, is that it's gRPC based. So it's a proxy you configure through an API. It's not. It has a configuration file, but it's a proxy that you can kind of live configure, and it will live reload its configuration. It's very popular in the service mesh world. Istio, the very popular service mesh tool, uses Envoy under the hood. But Envoy itself actually supports Wasm as a runtime environment where you can configure the proxy and then configure an external Wasm module and then tell the proxy when the requests come in, you pass the request to this module to process whatever that request is supposed to be doing, right? And they call them, in the Envoy world, they call them filters. So it's essentially an HTTP filter or gRPC filter that can pre-process or post-process your request. Pre-process means before it gets to the backend. Post-process means before it gets back to the client, right? So you have these like things. And then you have the new use cases is the cloud microservices. So that's essentially what Wasm is trying to do right now, is becoming a runtime environment for microservices. And these things kind of overlap between each other, right? So it's kind of an interesting world we're in. So runtimes. So to sum up everything I've said so far, you write code in whatever programming language you want. There are almost 40 programming languages that support compiling toward Wasm. You compile your code toward a Wasm binary. Your Wasm binary, typically, if you are doing containers or typical binaries, you will have to compile toward a specific target environment. With Wasm, it's a single Wasm binary. So you compile toward a specific single Wasm binary. Then you take that and you run it on top of a Wasm runtime, right? So the Wasm runtime is the thing that you have the choice between 40, 50, 60 of them. I lost count. There is a lot of them, right? Again, if this sounds very familiar to GVM, it is pretty much what the GVM was trying to achieve, right? The whole idea is that it's the same module that will run everywhere across CPU architectures. There are a lot of Wasm runtimes. These are the three maybe main ones. Wasm Time is the runtime from the Bytecode Alliance, that the alliance I talked about earlier. That's the group of people that are trying to create a standard for Wasm, right? There is Wasm Edge, which is a CNCF project. There is Wasmer. There is like tons of them, right? And then the WASI, or the WebAssembly System Interface, is essentially the added feature toward WebAssembly runtimes that is going to allow WebAssembly to become a backend technology. So that's I/O and network, right? So what it is, essentially, it's POSIX-inspired implementation or spec, right? So they're trying to do things like read and write from files, environment variables, hardware clocks, random sockets. Of course, I talked about I/O and system and file systems being the two major ones, right? Of course, there's quite a lot of interesting like other things that needs to be implemented. Like you need to implement random, you need to implement the clock, you probably need to implement NTP, like network time protocols. You need to implement a bunch of things to make basically WASI a useful technology, right? So this slide is old because there have been a preview 2 that was released recently. So if you're confused, what does preview 1 and preview 2 means? I don't know why, but Bytecode Alliance decided instead of calling things alpha, beta, GA, to call them preview 1, preview 2. Essentially, preview 2 is kind of like beta, right? For whatever reason, they decided we're not going to call it beta, we're going to call it preview 2. But the point here is that preview 2 is a spec. It's a set of implementation details that runtimes have to implement. So the Bytecode Alliance. So the reference implementation for the Bytecode Alliance is the Wasm Edge, Wasm Time, right? So they come up with the spec and then they implement it inside Wasm Time, and then they release the spec, and then it's up to the other runtimes to basically implement that spec themselves, right? Yeah, so there is quite a lot of still kind of limitations, proposals, stuff that have been implemented. Sockets are not yet there, by the way. So preview 2 only came up with file systems. So sockets or web or like I/O, network I/O are not there yet. There are some programming languages that support compiling toward WebAssembly as a target environment or a target compilation target. That's redundant. Target compilation or compilation target, but they do not support all the features that whatever that programming language support. Like forking, for example, you cannot fork a process in Wasm. That's just because of the security detail implementation that was invented in Wasm at some point. They decided that forking was kind of anti-security, and so in those like modern programming languages, that's not supported. There are projects that are trying to fix very specific implementation details. There's a project called WAGI, the WebAssembly Gateway Interface. I'm going to talk about it in a bit. And there is no garbage collection yet. So, you know, I think that Java people are not very happy about this. But there is a proposal. Anyway, so let's look at the demo. I think it's going to be interesting. So I have some code here. I'm going to show you. Let's do this, and then let's go to Go. Go Wasm, right? Good, okay. Just make this a little bit bigger. I have basically a very basic Go application here that is pretty standard. It just like says hello world, right? And I'm gonna show how we can compile this Go application to to a Wasm module, right? So let's do that. If you're a Go developer, this is all available in Go 21 release candidates, so it's still not part of the Go compiling or the Go compiler yet, but it's gonna come at some point eventually. And so I have my code which are written, and basically I just do this. Essentially, I just set an environment variable that says Go architecture Wasm, and I build my code the same way that any code can be built. And here I have my hello wasm .go and hello wasm.wasm, right? So this is the actual module itself. Let's open it. Yeah, pretty much not readable, right? And all I have to do is essentially just run it, right? So in my case, I'm using Wasm runtime, Wasm time as the runtime itself. And yeah, just nothing too fancy. Just run it, and it runs, right? So I can also do like maybe a Wasm Edge. Yeah, so Wasm Edge also works. So essentially, the idea of this demo is to show you that it doesn't really matter how you build your code. You can use any of the available or possible runtimes to actually run the code itself, right? Let's see if we can do maybe a web application. That would be interesting to do. Sorry? Yes, yeah, because the two runtimes I used, Wasm Edge and Wasm Time, they have like system like outputs, right? They have I/O implemented already. So these implement the tech preview 2 or the preview 2 version of the spec itself. It's a very boring demo, yes. Yeah, that's what I do. I do boring stuff, right? I mean, you know what my Twitter is. It's bored ABDEL, right? So then I can try to run this as oh, this is not running. Okay. All right, okay, so this is erroring for whatever reason. Yeah, okay, it's erroring because this version of the Wasm runtime I'm using doesn't have the sockets yet. So this is just trying to start an application that this has support 8080, but it's not there yet, so it's not gonna work, of course, right? I said something earlier. I said we are living in a world where WASI and Docker are kind of like coexistent together. So some of you might ask, why the hell do we actually want this, right? Why, if we are trying to use Wasm as a replacement, I'm putting replacement between quotes so no one can quote me on the internet saying that this is the future. If we want to use this as a replacement for Docker, why is it existing in Docker? And there is one very simple reason. It's because Docker itself already has a very rich ecosystem of existing modules, applications, frameworks, stuff like that. So Docker, the company, did jump on this occasion to say, okay, let's keep using Docker, but use Wasm as a compiling target so that the actual code running inside the container is just a Wasm runtime. So this is, I'm going to drink on this. It's just water. But this is where I'm going to blow your mind, right? So how many people here remember Docker shim? You know what a Docker shim is, right? OK, so I'm going to take you all back memory line a few years ago, right? Docker came out. Kubernetes came out, right? Kubernetes initially supported Docker. Following with me so far, right? Good. So Kubernetes supported Docker. Then eventually Kubernetes went, well, we don't want to only support Docker, we want to support other runtimes. So the Kubernetes project removed all the specific Docker code implementation inside Kubernetes and created something called the CRI, the Container Runtime Interface, right? Which was a standard interface that makes Docker support whatever runtime you want it to support, right? That piece of code that integrated Docker with Kubernetes was called the shim, which is essentially, you can think about it as a plugin or an extension, right? Good. Then Docker, with a bunch of other companies, they got together and they created something called the OCI, the Open Container Initiative, which was the project that was trying to, well, they managed to basically make a standard spec for containers. And they basically said, okay, this is the spec. We are going to have our own implementation. And whoever comes later and want to implement something that runs as a container, as long as they stick to the spec, which is the OCI, it will run. So today, you can take Docker, use it to build a container, and take another runtime, like Containerd, for example, and use containerd to run that Docker container, right? Because the container itself is according to the spec. So whatever runtime you want to use, you can use it, right? The part that a lot of people don't know is that containerd itself, when it was created with this idea of being a standard agnostic runtime. So containerd can run whatever you want. It doesn't only have to run containers. It can run whatever. So, and inside containerd, there is still a concept of shim, technically. Because since containerd itself is open, as in agnostic, and it can run containers, but you can also use containerd to run processes, right? It's kind of like systemd in Linux, right? You can use containerd to manage process, right? So they have this concept of shims, right? And so the part that is kind of mind-blowing, because a lot of people don't know this, is that today, if you have Docker on your laptop, under the hood, it's containerd. So Docker is the whole shebang of registry, container management system, multi-stage build, layering, all that stuff. That's all Docker. But once you do Docker run, you are technically just executing containerd under the hood, right? Following with me so far? Good. So what happened is that when Wasm was becoming a thing, the containerd community said, OK, we're going to just run a shim that would allow containerd to run Wasm, right? So essentially today, you can take containerd, take a Docker. So yeah, that's the other way around. You can take Docker, use Docker to build a container, take this container, and take containerd or Docker itself, and say, Docker run my Wasm module, and that will execute containerd, which then will execute the Wasm module through a shim. It's a very long explanation, because there's a lot of things happening kind of like the other way around. And I'm gonna plug a very shameless plug here. So in my podcast, our podcast, the Kubernetes podcast by Google, we interviewed one of the people behind containerd, and we went down for 1 hour talking about this in more details. So the episode is on the website. I highly recommend you listen to it, because there is a lot of interesting things that have been happening at the same time. And the person we talked to is called Phil Estates, and he has this like he have been involved for a very long time. So he has the actual history of how this whole thing evolved. And we even talked about this. This was before even I was interested in Wasm. And I was like, so how this container, it's very interesting. Let's just go listen to it. Anyway, so what I'm trying to say here is you can use Docker with its existing ecosystem to build containers, and then use Docker to run them. In essence, you're still using Docker as your command line. Inside of it, there is containerd, and inside containerd, there is a shim that will integrate with whatever Wasm runtime you have on your laptop. Make sense? I know this was a long explanation. I just want to leave you with this, right? Good. All right. So one of the implementation runtimes is called run WASI, which is again managed through containerd. But because containerd is trying to be very agnostic, they basically said, OK, we're going to implement a shim, and then you can plug whatever Wasm runtime into the shim, and then you do whatever you want. So starting 4.15, Docker through containerd can run Wasm Edge, Wasm Time, Spin. Spin is the framework by Fermyon, the company I talked about earlier, and a bunch of other frameworks. Again, this probably is even older. There is even an implementation in Azure AKS, so Azure Kubernetes Services, where they implemented run WASI through Spin, Slice, and Wasm Time. So today, I don't remember if it's beta or preview or GA. I don't think it's GA. You can basically run Wasm modules inside Kubernetes on Azure Kubernetes services. I think so far Azure is the only one that allows people to do this. And when you are running your Kubernetes workloads, you have to tag them. There is like an annotation called container runtime. You have to like add an annotation to your workload. But for you as a user, if you are used to use Kubernetes, you basically do kubectl get pods, and your Wasm module will show up as a pod, right? It is still a container running on a node, and as far as Kubernetes is concerned, it's still a container. It doesn't really matter, right? Yeah, so let's see. I could probably do this as I could show this demo. Again, all my demos are boring today, so stick with me. I think it's this one here. Yes, here we go. I can build this thing. Rust, Wasm, Docker, and then I can go into hello Wasm, and I can just build this as a container. Just basically, again, it's just a Rust app, and then inside of it, and then I have a Docker file, pretty straightforward. Even using like a Scratch container, it's not even like based on an existing container, and then I can just do this and run my. Oh, I don't have the. Okay, I don't have containerd. Sorry about that. Maybe I have this one. No, I don't have any of those. Okay, I don't have containerd configured here, so sorry about that. But essentially, yeah, it's essentially just like building a Docker container and running a Wasm module inside, and that's it. It's not really that fancy. So moving on, talking about WAGI and WASIX. So what is WAGI? WebAssembly Gateway Interface. It's essentially a project that is trying to implement a gateway interface. Essentially, you have a file called module.toml, and then that becomes the interface that basically receives HTTP requests through specific paths and can distribute them to various Wasm modules behind the scene. It's a fancy, it's a proxy basically with a gateway on top of it, right? It's not nothing too fancy. I don't know if I have a demo here, but probably I do. Yeah, I do. Here we go. This is just an example. This is how the configuration looks like. You just say what's the route that you want to forward to, and then the module you want to forward to, right? And it will just run the module and map your HTTP request to whatever backend you want. Sorry? I don't know what the detailed implementation is, to be honest with you. I have to look into it. I don't know. I tried it, and it was so unimpressive that I was like, okay, sure. I mean, you just re-implemented the proxy essentially, right? I mean, this is just a proxy, right? So, but this was implemented because of the lack of the sockets part, right? So this is like a very specific proprietary implementation until sockets are becoming, or the spec for sockets is out, right? And then there is WASIX. So WASIX is essentially like a marketplace of extended features that are missing in most Wasm runtimes. So you have all those implementations are proprietary to whoever implements them. Nothing is according to spec. This is all just people, again, nerding out and building stuff, right? So there's a file system support, asynchronous runtime support, forking, sub-processes, blah, 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 all that stuff. So there is, it's on wasix.org, and you can just look into it. Yeah, so we talked about WAGI a little bit, so I'm not going to do the demo. So if we talk about frameworks, I'm actually very close to the end of my demo, my talk here. So you have this thing called Spin. So Spin is built by Fermyon. If you use Spin, you can basically write code in the Spin framework and run it directly on Fermyon's serverless environment. So they essentially, it's a serverless environment. You give them code, they give you an URL, right? So that's essentially what it is, right? And then they have their own implementation of HTTP handling. The SDK itself is available in Rust, Go, and .NET. And yeah, that's essentially what Spin is. And if we talk about language supports, there is, again, as I said, like 40 plus programming languages that technically support compiling toward Wasm, but they all have kind of various stages of implementation. This slide is probably a little bit old, but you can see here what's kind of missing. Rust is probably the most advanced because they have a bunch of things supported. Go is probably supported in a newer version, not only 1.22. You can do JavaScript, you can do Java in there for those who like that. You can do Kotlin, you can do Python, Ruby. There's quite a lot of programming languages that support. Basically, all of these programming languages are supports compiling toward Wasm as a target compilation format in various degree of support in terms of features, right? And conclusion. Wasm outside the browser is fast changing. There's a lot of things happening. There is people working on it, and there is standards being built as we speak. There is probably still some level of maturity needed for this thing to become a viable backend technology. I give you a warning at the beginning of the talk. This is going to be nerdy, so just nerding about stuff. Will it replace containers? Maybe. We'll see. I actually saw last week an implementation where somebody was writing. I'm gonna go back a little bit to explain where this article came from that I read. You know, in this AI space we're in, right? We're all doing AI. We're all AI experts, right? There is two interesting things happening in this space right now. Training machine learning workloads is something we have been doing for a very long time, so we know how to do it. Where we are still struggling as technologists is inference. Inference is also a landscape which is moving super fast, especially with LLMs, right? There is tons of implementations, and it's essentially, moving down the highway 120 kilometers an hour while changing the tires. There is a lot of frameworks that are trying to do inference, and they all have some sort of implementation drawbacks, right? They all have, so like the most common thing in LLMs that a lot of people don't seem to realize is that a machine learning model, which is doing an LLM or an LLM model cannot actually process inputs and outputs at the same time. It does not know how to do parallelization, right? This is known. There is a lot of research done on this, right? So what all of these LLMs are doing is that they are batching inputs. So when you're sending inputs to an LLM, it will batch them and wait until a batch is filled up before processing it. And while it's waiting for the batch to fill up, it's processing outputs, right? And so I saw an article where basically they are using Wasm, or somebody used Wasm to write an inference server for an LLM. And they got some crazy, insane performance out of it, just because Wasm is super fast to start. The other interesting thing that Wasm is being used for in the LLM space is the fast runtime, the fast startup, right? Because it's super fast to start. And in LLM world, once you have all the model loaded into the memory of the GPU, if the runtime itself is pretty fast, then you can get like some insane performance out of that runtime. So again, this is just me researching things, being interested in how this thing is progressing. So it is exciting time. I think it's technology that is gonna progress over time. Again, not advising anybody to go rewrite all your application in Wasm, but go look into it. I think it's interesting, and I think there's a lot of good things that are gonna come out of this in the future. And that's it. Thank you very much. I hope